Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AMIRUL bin Muhammad AZAM, B0922102070. Today I would like to present to you about FEA analysis of bike frame. Next, this is list of member. Firstly, Muhammad AMMAR bin Muhammad MADZLAN. Second, Muhammad Danish Hazim bin ADNAN. Third, Muhammad AMIRUL bin Muhammad AZAM. And fourth, Muhammad AIZAT bin NORAZHAR. Next, for finite element analysis, FEA in structure engineering. What is FEA? Finite element analysis (FEA) is a numerical method used to simulate and predict the behavior of physical objects and systems under various conditions, such as stress, strain, heat, and vibration. The numerical technique displays complex geometry into smaller, manageable finite elements, allowing engineers to predict stress distribution, deforming pattern, vibration characteristics, and potential failure mode with remarkable accuracy. In modern practice, FEA enables visual prototyping that significantly reduces development time and cost while optimizing structural performance. The process involves modeling, meshing, applying boundary conditions, solving post-process and report. Software like ANSYS and Abacus.
So next for my turn, by the way, my name is Muhammad Danish Hazim bin ADNAN. My metric number is B09221040. So I will continue for objective and scope. So for our project has two primary objective. First, we aim to optimize the bicycle frame design to ensure it perform well across a broader spectrum of user weights. Second, we'll use finite element analysis (FEA) to study how stress is distributed across the frame and how it deforms under load. This insight will guide us toward a more robust and versatile design. So that to achieve our objective, our scope include three key tasks. For the first, we'll create a detailed 3D model of the bicycle frame, incorporating standard geometry and appropriate materials. Next, we'll explore ways to reduce weight without compromising strength and durability. Finally, we'll apply realistic static and dynamic loads to the frame to simulate actual reading condition, ensure our design is both practical and reliable.
Assalamualaikum. So we go to the next slide, which is problem statement. So bicycle frames face multiple complex loading conditions during real world use, such as road impacts and riders movement. Identifying areas of high stress and potential failure is crucial to improve safety and performance. This project aims to use finite element analysis, which is FEA, to evaluate stress distribution and critical failure points under different loading scenarios to guide better frame design.
First, for introduction to bike frame design analysis. Bicycle frame design have evolved from simple steel structure to advanced lightweight system using material like aluminum alloy and carbon fiber composite. As the core load-bearing component, frame must withstand complex static and dynamic load while optimizing stiffness for power transfer, complement for comfort, and minimal weight for performance. Modern analysis leverage computational tools like finite element analysis (FEA) to evaluate stress distribution and vibration characteristics. It also represents cost and physical prototyping. Current design challenges include balancing these competing mechanical requirements, improving aerodynamic efficiency, and developing sustainability material with industry standards like ISO 4210 ensuring safety through rigorous testing protocol. ISO 4210 primarily measures the safety and performance aspect of bicycle, focusing on factors like saddle height and testing procedure. Next, for finite element analysis (FEA) in structure engineering. What is FEA? Finite element analysis (FEA) is a numerical method used to simulate and predict the behavior of physical objects and systems under various conditions, such as stress, strain, heat, and vibration. The numerical technique displays complex geometry into smaller, manageable finite elements, allowing engineers to predict stress distribution, deforming pattern, vibration characteristics, and potential failure mode with remarkable accuracy. In modern practice, FEA enables visual prototyping that significantly reduces development time and cost while optimizing structural performance. The process involves modeling, meshing, applying boundary conditions, solving post-process and report. software like ANSYS and Abacus.
Alright, so there are several material that commonly used in bike frame. So the first one is aluminium. Aluminium has a lightweight and strong characteristic, and the price is at the mid range. For the second one is steel. Steel has a heavyweight characteristic, but it is durable, and for sure the price is affordable. And the last one, the most pricey one, is a carbon fiber. It has a feather light, but its stiffness is highest among others, and the price is expensive. Alright, so we go to the next slide, which is previous studies on FEA of bike frame. So there are several previous studies. So the first one is multi-material FEA in 2022. So their focus is static and dynamic about the bike frame, and the keywords of this research is stress below yield. So the second one is road frame comparison, also in 2022. So the focus is two frames under identical load, and the keyword for this studies is 164 megapascal versus 134 megapascal. And the third one is e-bike frame optimization in 2023. So their focus is fatigue safety, and the keyword for this studies is 19.6% fatigue improve. And the last one is bamboo frame FEA, so in 2024. So their focus is to find other alternative material, so they are use bamboo, and the keyword for this study is bottom bracket weak point. Alright, so we go to load conditions in FEA. So there are several load conditions in FEA, such as power pedaling, crash impact, and vertical impact. This is commonly cases in FEA. So the first one is power pedaling. So at 100 Newton to 500 Newton at bottom bracket while sprinting, and at the fix both drop out, and the critical zone is chain stays. The second one is crash impact. So basically 1000 Newton at head tube, which is frontal collision, and the fixed support is rear drop up, and the critical zone is top tube. And the last one is vertical impact, that in ISO 4210. So basically 2000 Newton and will at the front axle, which is stimulate pothole, and the fixed support is rear drop out, and the critical zone is on head tube and down tube injection. Alright, so as you can see, so this is my bicycle frame design, and this is a isometric view. So the first one is front view, at the bottom is top view, at the right is side view, and at the over is 3D view. Right, so we go to the next part, which is material data and view. But before that, I show you a bike frame with a mesh feature for structural steel bike frame.
Okay, now we are going to explain about the material data. For the material that we use for our bicycle, we are using the structural steel, which is mild steel. Okay, here are the properties for the structural steel. The most important ones are density, which is at 7,850 kilogram per meter cube. Next, the Young's modulus, which is at 2 times 10 to the power of 11 Pascal. Poisson's ratio, which is 0.3. And finally, the yield strength, which is 250. Now, this is our ANSYS analysis for our bicycle design. Firstly, for the stress distribution for static condition, the max equivalent stress is at 42 megapascal, and the max total deformation is at 0.0001632 meters. And finally, for the factor of safety, and the value for the factor of safety is 5.93. Okay, next is for the uphill condition. For the uphill condition, the max equivalent stress is at 7.65 Pascal. Next, the max total deformation for the uphill condition is 0.000082586 meters. And finally, for the factor of safety, it is at 3.27. And finally, for our ANSYS analysis for our racing bicycle is the downhill condition. For at the downhill condition, the max equivalent stress is at 1.03 Pascal. The max total deformation is at 0.000123 meters. And finally, for the factor of safety during a downhill condition on our bike, the factor of safety is 2.42. Okay. And next, this slide tells about the boundary modeling in FEA. So, we use fixed only realistic supports, such as the dropouts. Next, we use the spread loads. In ANSYS, we use the bearing load. And finally, we define the mesh at the junctions, such as at the head tube.
Okay, alright. So I want to continue about optimize and performance enhancements goals and key optimization methods. The primary goals of optimized bike frames are threefold. First are to reduce weight, increase stiffness, and improve the safety factor. Achieve this involve key optimization method. Firstly, topology optimization is crucial. It's a mathematical method that optimizes material distribution within a given design space for a set of loads and boundary condition. It's essential finding the best shape. Secondly, parametric studies allow engineers to systematically vary design parameter and evaluate their impact on performance. Finally, material optimization involves selecting the best materials or combination of materials for specific components to meet desired performance characteristic. So second, performance enhancement techniques. So I want to tell you about the performance enhancement techniques. To further enhance performance, several techniques are employed. Stress distribution analysis help in identify areas of high stress, concentration, and redistributing them for better load bearing. Natural frequency analysis is vital for understanding how the frame vibrates under different conditions, which impact like comfort and stability. And crucial, fatigue life prediction assessment, how long the frame will last under repeat stress, ensure the long-term durability. So in the practical step, in practice, the step for a project typically involve running and initial in FEA. So I want to tell about challenge and limitation in FEA of bike frames, about material properties and boundary condition. Firstly, bike frame often utilize advanced composite materials like carbon fiber, aluminium, or titanium. This direction-dependent properties making accurate modeling difficult and sometimes leading to inaccurate stress and deformation prediction in standard FEA software. The solution involves using advanced materials model and valid with physical testing. Secondly, apply realistic boundary condition. Is to bike loads are dynamic and multi-directional, from road bumps to pedaling force. FEA often idles this into static condition, which don't truly reflect real world effect. Dynamic analysis is crucial with careful valid of boundary condition. Second, safety factor and mesh sensitivity. Next, the safety factor present a challenge due to uncertain in load magnitude, material defects, and manufacture tolerance. Overly conservative design increase weight, while aggressive design risk failure. Probabilistic in FEA or in industry standard like ISO are key solution. Lastly, mesh sensitivity, significant impact accuracy. Poor mesh quality can lead to artificial stress concentration, a final mesh realistic increase miscritical stress. The approach here is to perform mesh convergence study to achieve that crucial balance between accuracy and computationally efficient. So for this slide, summary FEA bikes. Core purpose and static analysis. FEA is essential for balancing the competing demands of lightweight design, stiffness, strength, and ride comfort in bike frame. It helps engineers make informed design to choose. One key application is static analysis. This evaluates stress and deformation is under steady loads such as rider static weight or constant pedaling force. This allows for initial design iteration to ensure the frame can withstand typical. So next, dynamic and fatigue analysis. Moving beyond static, dynamic analysis is crucial. This simulates transient impact like road bumps, drops, and sudden force, which means are vital for assessing the frame overall durability and respond to real-world riding condition. Furthermore, fatigue analysis is indispensable. It predicts long-term failure that can occur due to cyclic loading such as repeat pedaling or constant vibration over extended use. This ensures the frame maintains its integrity and safety throughout the lifespan. In conclusion, in FEA, through its static, dynamic, and fatigue analysis capabilities, provide engineers with powerful insight to optimize bike frame design. It enables the creation of frame that are not only lightweight and stiff but also robust, comfortable, and safe, pushing the boundary of bicycle. So that's all from me. Thank you. So I want to tell about research gap FEA bikes. First, realistic dynamic load modeling and human bike interaction. Firstly, a significant gap lies in realistic dynamic load modeling. Most FEA studies use static or overly simplified dynamic loads, neglecting critical variability like road roughness and rider movement. The opportunity here is to apply advanced transition FEA coupled with multi-body to significantly improve the realism of simulation. Closely related is the human-bike interaction gap, rider biomechanics including pedaling force and subtle movement are often oversimple. Combining FEA with more detailed biomechanical modeling offer a path to truly realistic load simulation. Second, composite material behavior and optimized for additive manufacturing. Next, in composite material behavior, many FEA models assume uniform properties, ignore crucial fiber orientation effect in carbon fiber frames. This limit accurate failure prediction. Research into micromechanical modeling of composite is vital here to better predict failure. Finally, the gap in optimized for additive manufacture, many study lacks experimental valid for additively manufactured design due to cost and complexity. The opportunity is to apply topology optimized for lightweight, high strength additive design and integrate low cost sensor like strain gauge for better validation.